Vinod Kumare, studying in Sri Venkateshwara College of Engineering, Bangalore. Today I am going to discuss about a parallel transmission of power and data for electric vehicle dynamic wireless charging systems. Introduction to wireless charging system. Wireless power transfer technology is convenient, safe, and reliable. In recent years, it has been widely applied in various fields such as consumer electronics, biomedical implants, electric vehicle, and so on. Parallel transmission paves the way for future innovations and advancements in electric vehicle technology. By establishing a robust communication framework between electric vehicle and charging infrastructure, it enables seamless integration with emerging technologies such as autonomous driving and vehicle to grid systems. The seamless integration of parallel transmission with vehicle systems facilitates bidirectional communication, enabling electric vehicles to transmit essential data and receive commands for optimized charging. Central to the success of dynamic vehicle charging systems is the efficient transmission of both power and data. The seamless integration of these elements ensures not only for effective charging of electric vehicles but also facilitates real-time communication for monitoring, control, and safety purpose. The parallel transmission approach entails the simultaneous transfer of power and data streams, enabling continuous and uninterrupted communication between the charging infrastructure and electric vehicles. By integrating power and data transmission channels, this methodology optimizes the efficiency and reliability of dynamic wireless charging systems, offering numerous advantages over conventional sequential transmission methods. Parallel transmission enhances charging efficiency by minimizing latency and maximizing throughput. This concurrent transmission of power and data eliminates the need for time-consuming handshakes between the charging infrastructure and electric vehicles, resulting in faster and more seamless charging experiences. Objectives of the system: to understand the how the parallel transmission of power and data for electric vehicles, to develop comprehensive strategies and solutions to leverage parallel transmission for optimizing power and data transmission, to employed in consumer electronics and IoT devices, to utilize in developing wireless charging infrastructure for public spaces. Applications of this electric vehicle charging system: it can be applied in short range vehicle wireless power transfer contexts, utilized in developing wireless charging infrastructure for public spaces. It can be applied in short range wireless power transfer contexts, employed in consumer electronics and IoT devices, ideal for dynamic and varying load conditions, found in grid tied renewable energy systems. Advantages of these wireless charging systems: demonstrate high efficiency in power transfer, presents effective cost and straightforward design, adaptable to drives and load conditions, address efficiency and power quality concerns, offers flexibility for different power transfer scenarios. Disadvantages of these wireless charging systems for electric vehicles: encounters challenges related to bulky design, limited in terms of power transfer range, vulnerable to variations in load conditions, introduces complexity with the inclusion of multiple stages, complexity in mode switching control, requires a balance in design for optimal performance. Methodology used in the dynamic power and data for wireless charging electric vehicles. In dynamic wireless power transfer system, the transmitter power pad is energized based on the in-motion vehicle position alignment. By concerning speed is the complex parameter. The charging infrastructure of the electric vehicle charging system is developed for specific distance to charge the electric vehicle within a durable time. This period is similar to the transient condition. In the dynamic wireless power transfer charging system, the magnetic resonant coupling between the primary unit and the secondary power pad unit introduces the misalignment tolerance in the longitudinal and latitudinal axis. This misalignment tolerance will affect the power transfer for electric vehicles in some cases. It undergoes the PNP effect. This misalignment challenges can be addressed by improving the magnetic wireless coupler power coil geometrical structure and selecting a proper resonant matching network. Block diagram of the electric vehicle wireless charging system. The expenditure factor of the wireless charging system depends on the initial cost of the WRIPT system development, including the size of the charging station infrastructure with number of the wireless power transfer charging units. The cost benefits depends on the number of users utilizing the charging infrastructure. The utilization of the wireless power transfer charging systems benefits in the reduction of the battery capacity or need for the battery storage system. The seasonal factors that and the environment that depend on the geographical location will affect the lifespan of the wireless power transfer charging infrastructure. This is the block diagram of the wireless power transfer charging systems for electric vehicle. It consists of two parallel metallic plates separated by dielectric medium or air serving as an interface medium between the plates. The entire system is activated by inverter of high frequency generating an electric field between the plates. This electric field in turn initiates the flow of current between the plates, facilitating the transfer of power. This operational principle underlines capacitive charging and in practical charging scenarios. This method relies on create power electronic circuits, inverters, rectifiers, and similar components. Wireless power transfer is a technology that enables the transmission of electric energy from a power source to an electric load without any physical connections. Compression topologies in WPT plays a crucial role in achieving efficient power transfer. Here are some common comp compression topologies used in WPT. The main components of the wireless charging system are analyzed. One of these components is molded on the road and other is molded on the bottom of the car. The transmitter component is fixed to the road and the moving part of the WPT system is fixed to the car. Resultant discussion of the system. The implementation of parallel transmission of power and data for electric vehicle dynamic charging system demonstrated and significant improvements in efficiency, real-time monitoring and control, integration with vehicle systems, reliability, scalability, flexibility, and cost effectiveness. This results in highlight the potential of the parallel transmission to drive the whispered adoption and integration of sustainable transportation solutions, paving the way towards a greener and the more sustainable future. This scattering around the coil was observed to be more intense. This magnetic scattering can be directed or blocked by using core and shading. Several studies illustrate the CPT using multiple capacitive plates with phase shifts to minimize the bridging effect. Conclusion of this wireless charging system. A parallel transmission of power and data for dynamic wireless charging system offers significant advantages in terms of efficiency, real-time monitoring and control, integration with vehicle system, reliability, scalability, flexibility, and cost effectiveness. The adoption of parallel transmission of power and data for electric vehicle dynamic charging wireless charging systems represent a significant step towards realizing the full potential of electric mobility. The seamless integration of parallel transmission with vehicle system facilitates bidirectional communication, enabling EVs to transmit essential data and receive commands from the charging system. These are the references for the dynamic wireless charging system for electric vehicles. Thank you.